Okay, hi everyone. We're back and we're going to today talk about the second module, in which we'll present fields, the concept of fields, and the concept of vector spaces. Both of these concepts are very important for the kind of linear system structure that we're going to do in this course. Namely, it's going to be very important for us to assign what's called a vector space structure to the individual sets, the spaces that we're going to be interested in operating on with our linear systems. So all of the concepts that we're introducing in these linear algebra modules at the beginning are going to have their counterpart as we move into linear system theory later. Okay, so let's start with the concept of a field. Now, first we'll define a field, and then we'll use it in our definition of a vector space. So what is a field? We use this notation, it's called blackboard when we have this double line here. So blackboard F is the field. And to be precise, we define a field as a set of objects, a set of elements, and then two binary operations. Those operations we typically call multiplication and addition. And typically for fields of spaces that we're used to, this is just regular addition and multiplication. Where it becomes interesting is when we're looking at fields of objects that are not standard, that are not the usual things that we deal with, like the real line. Okay, so a set of objects, an operation which we'll call addition, and an operation, this dot, which we call multiplication. And then the following rules have to be satisfied. So the field is defined in terms of these rules. The associative property. So the field is associative, which means that if you take any elements, alpha, beta, and gamma in the field, and you apply, so actually we're talking first about this addition operator. So in the field, the addition operator is associative, which means the following. You can add A and B together, and then add gamma to it, or alpha and beta together, and then add gamma. And that's the same as adding alpha to the sum of beta and gamma. So you can do this operation first, and then add alpha. Other properties that we have to satisfy. Commutative, which means that alpha plus beta is equal to beta plus alpha. It doesn't matter what order you apply this, in what order you do the operation here. So you can switch the elements around the operation that you're performing. There exists an identity element. So we call that element 0. There exists an identity, and these are all for addition. So the identity element under addition is known as the element 0. And it satisfies the following rule, that if you add this identity element, so under this operation, to any element in the field, in the set F, then you get back the element that you started with. And there exists an inverse. Once you've defined the identity, you can define an inverse. So what we say is for all alpha elements in the field, so for any element in the field, there exists an inverse, which we'll call minus alpha here, such that alpha plus this inverse gives us back the identity element. Okay, very standard. We're used to this in standard addition. We have a set of rules for multiplication. So multiplication is associative. We don't need to go through what that means. It's the same as in addition, except we're using the multiplication operator. So that's the dot here. It's associative, it's commutative. So this is the property 5, property 6, commutative. There exists an identity element. So the identity under multiplication, it has to give you back the same thing you started with. So we say there exists an identity, we'll call it 1, because that's what it is in standard multiplication, such that alpha times 1 is equal to alpha. And there exists an inverse. The inverse element under it's the inverse under the multiplication operator which gives you back the identity. So for all alpha not equal to 0, so the 0 is the identity element under addition, there exists an inverse, we'll call that alpha inverse, such that alpha times alpha inverse is equal to the multiplicative identity 1. And then finally, we combine these two rules. So we say that multiplication distributes over addition. Distributes over addition. And that just means what it says, so that if you have 3 elements in the field, alpha, beta, and gamma, alpha times beta plus gamma is equal to alpha times beta plus alpha times gamma. And that commutes itself as well. Okay, so that's the definition of a field. And some common fields that we're used to are things like the real numbers, examples. The field of real numbers under the standard definitions of addition and multiplication. The set of complex numbers under the set of the rules for addition and multiplication of complex numbers represents a field. The field of rational functions with coefficients that are real numbers. So we use this notation to represent rational functions in S whose coefficients are real numbers. So things like s squared plus 2s plus 1 over s plus 3. That's a rational function. Its coefficients are real numbers. And the set of all rational functions whose coefficients are real numbers represents a field. And so we define, for example, the identity element, all of these identities and inverses for those sets of functions. Things that are not fields. So if we look at something similar to the previous, but we put a restriction on it. So we use these square brackets to represent the field, or the set of polynomials, the set of polynomials whose coefficients are real numbers. That set does not represent a field. It's not a field because there's no multiplicative inverse, which gives us back the identity element. If you have a polynomial and you try to think about the inverse of that polynomial, which naturally would be 1 over that polynomial, that inverse is not in the set of rational polynomials. So implicit in this definition is that, like, when we say there exists an inverse or there exists an identity, that means that there exists an identity or an inverse inside the set of elements itself. And so here, in order to get a multiplicative inverse, we had to go outside of the field. We had to look at something that was not a polynomial function. So polynomials in S with coefficients that are real numbers that does not represent a field. Okay, so that's the definition of a field, and from that we can define what we mean by a vector space. So typically when we're looking at vector spaces, we're looking at combining a set of elements that are vectors with a field that, and typically in this course, we're going to be using the field that is the real numbers. Sometimes we'll use complex numbers, but sometimes we'll use something a little bit more complex. Okay, so with that definition of a field, let's move on to a vector space. And so we use, again, interchangeably the terminology vector space or linear space. So we use this terminology interchangeably, linear space. And again, it's a little dry because we have to define what it is, but it becomes interesting when we use it. So let's persist with this. So we define a vector space, VF, as a set of elements, V, and we're going to call those vectors, and an associated field F. And this field it satisfies, of course, all the properties of a field. And then associated with that, not just the spaces, but we also associate two operations. And don't be confused, but I'm going to use the same notation that we used for a field. So we have a plus, but now this means vector addition. And we have a dot, and now this means scalar multiplication. So that plus means that it's the operation that I'm going to apply to two vectors to get another vector. And this multiplication means I'm going to take a vector and multiply by an element of my field, which we'll loosely call scalars. That's typically what the field elements are called when it's associated with a vector space. Okay, so again, we have properties that we have to satisfy. So this is the vector space, and addition and multiplication have to satisfy several properties. So addition plus is associative. Associative, we know what that means. But let's just write it out because now we're operating on vectors. So it means if you look at three vectors, x, y, and z in your vector space, then this associativity rule holds. So it's the same rule we had before, but now we're just careful. These are elements. So here, rather than being elements of the field, they're elements of the set of things that we're going to be calling vectors, V. Commutative, associative. Addition is also commutative. You can change the order of operation. There exists an identity element under addition. And we're going to use this terminology in this course, theta, to represent the zero vector. And so similar to previous, and then we also have an inverse. There exists an inverse. And so what that means is if you look at any vector in your vector space, any vector x, there exists a vector which we'll call minus x, such that x plus minus x gives us back the additive identity, the zero vector. And then scalar multiplication. So scalar multiplication, we have a set of rules for. Scalar multiplication is, well, it satisfies the following properties. If you take two scalars, alpha and beta, and you multiply them together using the operation from the field, and then you multiply that by a vector in V, x, that's equal to alpha times beta x. Okay, so the operation here is the operation from the field, and the operation here is this operation. So this is multiplying a vector by a scalar. Similarly, here we have the scalar multiplication in the vector space. So we're multiplying a scalar by a vector, and then we take that product and we perform that operation again, multiplying a vector by a scalar. And then similarly, we have the identity and the inverse elements. So 1 times x is equal to x, and 0 times x is equal to the 0 vector. And here, 1 and 0 are the associated identity elements from the field, so from the field F. And then finally, we have the distributed laws, distributive. And so basically what that we can say there is if we look at elements alpha plus beta from the field, multiply by x, we get alpha x plus beta x, and vice versa. So basically what we're saying here with all of these properties is that the vector space is closed under vector addition and scalar multiplication. Closed means that if you perform those operations on elements of the space, you get back something in the same space. You can't go outside the space when you're performing those operations. Let's conclude with some brief examples of vector spaces. So some of these are very familiar to those of you who have had linear algebra, but standard examples. So we often think of the space of vectors Rn. In fact, we spend a lot of time with the space of vectors Rn over the field of reals, with the standard definitions of addition and multiplication for vectors. So this is a vector space. So we'll basically write it as we have here as Rn R. And then we don't typically write plus and times because it's assumed that we're using those operations from the standard, from the space itself. So standard addition and multiplication for those vectors. In general, we can, so this is a vector space, we can replace the R with a complex, C, and we can look at the space of vectors whose elements, so n vectors whose elements are complex numbers, over the field of complex numbers. And this is also a vector space. But where we have to be careful, so if we looked, for example, at the space of vectors whose elements are complex numbers over the field of reals, we'd still get a vector space. But if we looked at the space of vectors of real numbers, so Rn, over the field of complex numbers, this is not a vector space. Because as soon as we start to think about scalar multiplication and we take a vector and we multiply it by a complex number from our field, we'll get something that's outside of Rn. In particular, it will be in Cn. So this is not closed under scalar multiplication. And let's conclude with one more maybe non-standard example. So these are typically what we look at when we look at vector spaces in this course, but we'll also spend a lot of time with vector spaces where the vectors are actually functions. So we'll conclude today's module with an example of a function space. Okay, so the function space and we'll write it as F. So the set of functions which maps a set D to a set V, where V is a vector space, so VF is a vector space over an associated field. That space here, using the same field as V has, is a vector space. So the set of functions mapping a set D to a vector space V operating over the same field as is associated to V is a vector space. So continuous functions that map an interval of the real line to Rn, for example, where we're using the real numbers as our scalars. Differentiable functions. We can think about subclasses of these functions that inherit the properties of a vector space. And so this definition of vector spaces is quite general. We're familiar with it because we're used to dealing with vectors in Rn and the scalars in R. But the actual definition and the properties of a vector space are important to internalize, because if we're thinking about operations on functions, which we will be doing a lot of in this course, then it's important to be able to put a vector space structure on those functions so that we can do mathematics on that vector space. Okay, so throughout the next several modules, we'll come up with some examples of function spaces which are vector spaces. And I think to conclude this module, we've talked about fields, we've talked about vector spaces, we've done a couple of quick examples. I think to conclude this, we should think about if somebody gives you a space and they say, show me that it's a vector space. Usually it's quite easy to show that these properties of associativity and commutativity hold. The hard part is, or the part that's usually the crux of it, is to show that that space is closed under the operations of vector addition and scalar multiplication. So that's where we typically spend our time when we're showing that something is a vector space. Okay, so with that, we'll conclude knowing that we now have a clear definition of field and thus a definition of vector space. Thank you.